we are going to start with the displacement analysis of open kinematic chains. So, essentially displacement analysis of robots. So, remember that robot is a mechanism with 2 or more degrees of freedom, that is how we have defined robots. So, we are going to look at displacement analysis of robot manipulators, the problem of forward and inverse kinematics, and we will demonstrate this analysis with the example of an RR open chain manipulator. So, let us look at our plan for displacement analysis of robots. We will start with planar robots. We will look at these open chain planar robots. Later on, we are going to also look at closed chain planar robots. So, this is our plan. So, we will start off with open chain planar robots. Now, as you know that displacement analysis has two problems. The forward kinematics problem states that given the actuator input, there can be multiple actuators. So, given the actuator inputs, find the output. The inverse kinematics problem states that for a specified output, which may be position or position and orientation of an output link, find the actuator inputs. So, the inputs are the actuator displacements and the output is the end effector position and orientation in the case of robots. So, under open chain planar robots, we are going to look at certain examples. Today, we are going to look at in this lecture the example of a 2R planar robot. So, this is a 2R planar manipulator. If you calculate the degrees of freedom, so you have links as a ground link, this and the third link. So, there are 3 links, number of kinematic pairs, you have 1, 2. So, therefore, degree of freedom is equal to 3 times number of links minus 1 minus 3 times number of joints plus summation of degree of freedom of individual joints. So, we will directly write it. You have 2 revolute pairs, as the name suggests, we have 2 revolute joints. So, each revolute joint has 1 degree of freedom. So, their summation of the total degrees of freedom is 2, therefore, this turns out to be 2. So, this has 2 degrees of freedom. So, this qualifies to be a robot, and because it has 2 degrees of freedom, it will require 2 inputs to be specified. What are these inputs? This angle theta 1 and this angle theta 2. Okay. Now, note that theta 1 is being measured from the x axis, the ground fixed x axis. Theta 2 is being measured from the line of link 1 or this link 2. So, theta 2 is being measured as an angle between the second link and the third link. Theta 2 is not measured from the horizontal axis. Theta 2 is being measured from the line of the second link. So, since we have two inputs and two outputs, what are the outputs? These are the position and orientation of the end effector point. So, end effector can move in the xy plane. So, these are the 2 degrees of freedom, and there are two inputs, theta 1 and theta 2. So, the forward kinematics problem states that given theta 1 and theta 2, find out the location of the end effector. So, given theta 1 and theta 2, find out the position of the end effector. So, that is the forward kinematics problem. So, here I have this axis, I have these angles defined, theta 1 and theta 2. Now, suppose I want to express the x coordinate of the end effector. So, which means this is the x coordinate of the end effector. Now, that you can very easily see is this distance plus this distance. So, summation of these two, so that is x e. So, summation of these two distances is x e. Now, this distance, the first one, it is very easy to see that this is L1 cosine of theta 1. So, cosine I am writing as c. So, L1 cosine theta 1 and the second distance. So, let me draw a horizontal line. So, this is parallel to the x axis. You can very easily see that this is theta 1, because this line is oriented with link 2. So, this is theta 1 and this is theta 2. So, this distance is nothing but L2 cosine theta 1 plus theta 2. So, therefore, our x e is L1 cosine theta 1 plus L2 cosine of theta 1 plus theta 2, that is x e. What about y e? By similar manner you can see this is y e. It is summation of these two distances. This is the first distance and the second. Now, this distance is very easy to see is L1 sin theta 1, and this distance is L2 sin of theta 1 plus theta 2. Therefore, YE is L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. So, we have expressed our outputs XE and YE in terms of our inputs theta 1 and theta 2. In addition to this, in certain applications, I might require this angle phi. In certain applications, we might require this angle phi. This is the angle of orientation of the end effector. So, the orientation of end effector, that angle I am measuring again from the x axis, from the horizontal axis, and phi is that angle of orientation. So, this might be required when, for example, if the robot is going and trying to grasp at a certain angle. So, the orientation at which it grasps might be of importance. We might want to know that angle. So, it is not difficult to see that this orientation angle phi is, so this is the orientation angle, nothing but theta 1 plus theta 2. So, that is the orientation of the end effector. Our forward kinematics problem is already solved here. The problem that we had set out to solve is solved here. This is in addition, we have the orientation of the end effector, which might be necessary in certain cases. So, this is the forward kinematics problem. So, let me formally now show you. So, the end effector position coordinates XE and YE are given by these expressions. The end effector orientation coordinate phi is given by theta 1 plus theta 2. Now, the inverse kinematics problem. So, what is the statement of the inverse kinematics problem? So, what are we given? We are given the position of the end effector. So, we are given this position x e y e, which is the coordinates, which are the coordinates of the end effector. And what do we have to find out? We have to find out the angles that result in the specified position or the required or the desired position of the end effector. So, we have to find out these angles theta 1 and theta 2, so that the end effector can be positioned at x e y e as shown. Now, let us again begin with the forward kinematics expressions. So, here I have x e, the x coordinate of the end effector in terms of theta 1, theta 2, and I have y e in terms of theta 1 and theta 2. So, therefore, x e minus L 1 cos theta 1 whole square plus y e minus L 1 sin theta 1 whole square must be equal to L 2 square, because this gives me L 2 cos theta 1 plus theta 2 whole square plus this gives me L 2 sine of theta 1 plus theta 2 whole square. So, where I have written C as I have written C for cos and S for sine. So, the sum of squares of these two, and that is L 2 square. So, what is our problem? Problem is given x e and y e, we have to find out theta 1 and theta 2. Now, I have this expression. So, let me open up. So, x e square plus, now from the first square I will get L 1 square cos square theta 1, and from the second I will get L 1 square sin square theta 1. So, I can write L 1 square plus from the second square I will get y e square. Then we have the cross terms, twice x e L 1 cosine theta 1 minus twice y e L 1 sine theta 1 is equal to L 2 square. So, once again let us remind ourselves, we are given x e y e, we have to find out theta 1. So, this expression that I have written out, I can rearrange like this. So, x e, or I will start with y e sin theta 1. So, I am taking these expressions on the right hand side. So, and dividing by 2 L 1. So, y e sin theta 1 plus x e cosine theta 1 must be equal to x e square plus y e square plus L 1 square minus L 2 square whole divided by 2 times L 1. So, this is what we will obtain, and you can see that this can be expressed or written in the form a sin theta 1 plus b cosine theta 1 is equal to c, where a, b and c have these terms x, c, y, e, which are known. So, x, c, y, e are known, and therefore, a, b, c are known. So, the only unknown in this red equation is theta 1. So, let me formally write this out. So, here we have this equation where A, B and C are completely known because we know x e and y e. The only unknown is theta 1. So, we have to solve this equation A sin theta 1 plus B cos theta 1 equal to C. Once I have theta 1 as a solution from this equation, I can now find out theta 2. How? This is what we do. This is the location of the end effector. So, x e y e So, I have dropped a vertical and drawn a horizontal. So, this is a 90-degree. This angle, this total angle of the right angle triangle is theta 1 plus theta 2. So, tangent of theta 1 plus theta 2 is nothing but this distance divided by this distance. Now, this distance is y e minus L 1 sin theta 1 and this distance is x e minus L 1 cosine theta 1. So, tangent of theta 1 plus theta 2 is the ratio of these two terms. So, once I have solved for theta 1 from here, I can substitute in the second equation and solve for theta 2. So, we again reiterate the solution of A sin theta 1 plus B cosine theta 1 equal to C. So, we make this substitution as we have been doing, x as tan theta 1 by 2 and expressing sin theta 1 and cosine theta 1 in terms of tan theta 1 by 2, which is x, and substituting these expressions in our master equation, we finally obtain a quadratic in x. The solution of this quadratic equation is given here. There are two solutions, as you know. So, two solutions which are given by this plus and minus. So, just to recall, A, B and C are completely known, x e and y e, they are known to us. So, I can find out tan theta 1 by 2. There are two solutions of tan theta 1 by 2. So, here are the two solutions of tan theta 1 by 2, which are obtained. So, theta 1 has two solutions, theta 1 1 and theta 1 2. I have taken these two signs, once I have taken the negative, the other time I have taken the positive. So, I have the two solutions of theta 1. Once I have this theta 1, I will substitute this theta 1 1 and theta 1 2 1 by 1 and I will calculate. Here also I have to substitute. So, here is where I substitute theta 1 these 3 places and I solve for theta 2. And once again, when you do it on a computer, you can use this inverse function a tan 2 to get the quadrant correct. So, let us understand the solutions graphically. What is specified? We are specified x c and y e. So, we are specified this location is fixed. This location being fixed, we want to find out where this hinge goes. Now, L2, the link L2 therefore can now rotate about this fixed x e y e point, and link L1 can rotate about this fixed ground hinge. So, these are the 2 circles. So, the intersection of these 2 circles are the solutions. So, one solution is shown in this black, the other solution, let me draw out. So, the other solution is at this intersection. So, here and here. These are the 2 solutions. So, one is the black configuration, the other is the blue configuration. So, these are the 2 solutions. So, you can notice the difference in these 2 configurations is the orientation angle phi. The difference is the orientation angle phi. So, in the first configuration, this is phi. In the second configuration, this is phi. So, the orientation at which the manipulator reaches that position x e y e are different. The orientations are different. So, depending on the requirement, you can choose one of the solutions. Now, the workspace. What is the reach of the end effector of the manipulator? This is an important question. So, as you know, I have drawn it out here for you. The second, so this is link 2, this is link 3, one is of course the ground. So, the second link can rotate and the hinge point goes on this circle. When the third link rotates, the end effector point moves on this circle. So, what is the farthest reach of the manipulator? Farthest reach is when I have the completely extended situation of the arm. That is the farthest reach. What is the nearest reach? When I have the folded configuration. So, this is the extended configuration, and this is the folded configuration. So, the extended configuration and the folded configuration. So, with these two I can now draw the workspace. So, this light blue shaded region is the workspace of this manipulator. So, it can reach any point in this shaded region. It cannot reach in the exterior, neither can it reach, there is a region in the interior which cannot be reached. So, there is an annular region which can be reached by this manipulator. Now, there are other constraints. So, this is ideally, I mean this is what kinematically the workspace looks like, but actually the workspace can be much smaller than this. Why? Because these motors which actuate the joints, they can have joint limits, either because of physical construction or because you have some obstructions. So, for example, if this second joint can vary only between these two angles, then the workspace can be further shortened. So, the workspace so it can go either like this or up to like this. In that case, the workspace is between these two limits. So, this inner blue circle and the outer blue circle. There can be further limits. For example, the inner joint can have a limit. So, you can have various possibilities. So, for full rotation, this is the workspace. Under joint limits, restrictions on joint rotations, the workspace can reduce substantially. So, this is a point which needs to be analyzed for an individual robot. So, let me summarize. We have looked at the displacement analysis of robot manipulators, we have looked at the forward and inverse kinematics problem, and we have demonstrated our analysis through the example of a 2R open chain planar manipulator. So, with that I close this lecture.